In this example, we're told that we have a 635 nanometer wavelength red laser that's shining on this double slit arrangement. And presumably we're going to get the usual alternating pattern of bright, dark, bright, dark, bright, dark, and so on, above and below, a symmetric pattern. So we're going to get bright spots and then dark spots in between those. And of course, in the in-between regions between a bright spot and a dark spot, we're going to get a continuous gradient of bright, kind of dark, dark, kind of dark, kind of bright, and so on. So we get this continuous smooth change between bright and dark and bright and dark. The in-between zones are going to be partial interference. And we are specifically told here that the first diffraction minimum, that is the first dark spot, occurs at an angle of 10 degrees to the original beam. I assume the original beam means just straight across. So we can assume that the first minimum is 10 degrees offset. So that's what we would call theta. And we want to know, based on that information, what is the distance between the slits, this little d, the slit separation. So to figure that out, what's one equation we could use to link all this information together? Do we have any equations describing, in terms of angle, where these bright and dark spots appear?
Would it be like the equation with like delta y and I'm not entirely sure, but it was like with delta y and there was like an uppercase d and a lowercase d.
If we had distances, I would use that one. Like if we knew the distance from bright spot to dark spot or something like that, and we knew the distance from, the big D would be the distance from the slits to the screen. So if we were dealing with those distances, like if we were told how high in terms of centimeters or whatever, and how far apart these were in terms of centimeters or meters or whatever, then yes, I would use the equation with the distances. But in this case, we're not given distances, we're given an angle. So we can actually use the original, the d sine theta one, the one using the angle. And typically we get constructive interference when d times sine theta equals a whole number times the wavelength. We get destructive interference when d sine theta equals something and a half wavelengths. Because the d sine theta ultimately tells you geometrically how much further one of the waves is traveling. If you're looking at, for instance, some location up here, you've got a wave traveling or a ray traveling from the first slit to this location, and another ray traveling from this slit to this location. Those waves are traveling different distances. One of them is traveling a little bit longer. The d times sine theta tells you how much longer one of the waves is traveling. So that d sine theta is the delta x, the extra path length difference. If that difference in path length is a whole number of wavelengths, then your waves are offset by a whole number of cycles. So you get constructive interference. If the difference in path length is something and a half wavelengths, that's something and a half cycles, so you get destructive interference. Based on the information we know, should we be looking at this as constructive or destructive?
Destructive?
Yeah, this is destructive interference because we're looking at a minimum. We're looking at a dark spot. So using this equation, we could write out d, which we don't know, that's what we're trying to solve for, times sine of 10 degrees, that angle of elevation there, equals, and what would we use for n here if we're looking at this bright spot, or sorry, this dark spot? Destructive because the problem we're looking at specifically says we have a diffraction minimum. The first minimum, that is the first dark spot, appears at this angular location. So this thing here, if we think of this as how offset they are, the central maximum has no offset at all. So that's n equals 0. The next bright spot would be 1 wavelength offset, then 2 wavelengths offset, then 3 wavelengths offset. So the in-between points, n plus 1/2, presumably this is going to be 1/2 wavelength offset. Technically, I would say n is 0, because we've got 0 plus 1/2 gives us 1/2 as how many wavelengths offset. So technically, for the first minimum, we're using 0 as n, because we're half a wavelength past n equals 0. So overall, this is going to be 1/2 times the wavelength. And we know what the wavelength is. That's the 635 nanometers. So d times sine theta, the usual delta x for the double slit experiment, equals 1/2, because this first dark spot should be exactly half a wavelength offset times the wavelength. And then what's the only thing we still need to do to solve for d? Yeah, divide both sides by sine of 10. So we get 635 nanometers divided by 2, and also divided by sine of 10. Punch that into a calculator, and that should tell us the distance between slits. So I'm getting about, 1,828 nanometers. So that would be the distance between the slits here. Any questions on that? This was specifically from problem 1 on what's labeled quiz 2. Quiz 2, Q2A. Any other questions on that? All right, then let's take a look at standing waves. Standing waves are also essentially a form of interference, but not in the usual way. Usually for interference, we expect we have waves from 2 sources that are interfering with each other because they're occupying the same space. A standing wave is a little different. A standing wave occurs when you've got a wave that's approaching some sort of barrier and bounces off. And then you've got the original incoming wave and its own echo interfering with each other. And this doesn't really happen if you just got like a single pulse. Like if you just snap your fingers and that sound echoes off a wall, this doesn't really happen. But if you've got a continuing wave, like if you've got something continuously producing a sound, that sound keeps going out, and eventually its echoes start coming back from maybe it hits a wall or something. So you've got the outgoing sound from the source and its own echo occupying the same space at the same time. So that's going to cause interference between the sound and its own reflection. This generally tends to happen if you've got a wave occupying some confined space. Like maybe you've got a long hallway that's capped at both ends, and you're inside that hallway singing or playing a musical instrument or something. You're creating this sound, it's bouncing off one wall and bouncing off the other wall. So you've got sound bouncing back and forth, interfering with its own echoes. And what this tends to create is certain zones, certain regions that always have constructive interference, and certain zones that always have destructive interference. And this leads to this repeating pattern that forms a very stable, very loud sound, if the note is just right. Any questions on the general idea so far? Yeah, go ahead. The n in the double slit experiment? The n in the d sine theta equals n lambda. The n is basically just keeping count of which bright spot we're talking about. So with that pattern of bright and dark spots, we had a bright spot at the very center. So like directly across from the slits themselves. That central bright spot, the central maximum, is n equals 0. The next bright spot is n equals 1. The next bright spot is n equals 2, and so on. And then the bright spots below the center you could treat as n equals -1, n equals -2, and so on. Formally, what n is keeping track of is how many wavelengths offset the distances are. For instance, at the center, the two rays from slit 1 to the destination and from slit 2 to the destination, they're traveling the same distance. So the difference between them is 0. But if you take a look at bright spot number 1, if you trace this ray of light and this ray of light, they're traveling different distances. One of them is a little bit longer. That little bit of extra distance is exactly 1 wavelength, which is why we call this n equals 1. It's 1 wavelength of difference. Or if you take a look at the next one, if you trace out this ray from slit 1 to the destination and this ray from slit 2 to the destination, if you take a look at the difference in the paths, the longer path is exactly 2 wavelengths longer than the shorter path. So you could think of n as keeping track of how many wavelengths longer the longer path is. You could also look at it geometrically as just counting up which bright spot we're looking at. This is the center. This is the first bright spot from the center. This is the second bright spot from the center, and so on. So visually, that's what n is keeping track of, which bright spot we're talking about. But in terms of the physics behind it, it's also keeping track of how many wavelengths offset the two paths are. Any other questions on that one?
No, I think that's good. Thank you.
All right, that's good. Then let's take a look at some standing waves. And I think that probably the most easily visualizable standing waves are waves on a string. That is a confined space. If you've got just like a guitar string stretched out and tied down at both ends. Like if you just take a couple of nails and stretch, like tie a guitar string to one nail, stretch it out, tie it to the other nail, and stretch it tight. You now have a string. You could pluck the string, creating oscillations, a wave that's confined to this finite space. So if we take a look at standing waves on a string, and we usually describe this as a fixed string. And that's fixed as in fixed in place. The ends cannot move. The left end is fixed in place and cannot move. The right end is also fixed in place and cannot move. As opposed to a free, I mean, this doesn't really work for strings. If the ends of the string are not tied down, the string is just going to be loose. You don't really have any tension in it. But you could have another solid object that's open on, that's free to move on both ends, like a xylophone, for instance. A xylophone consists of just long, flat metal bars that are loosely balanced on a couple of pegs. But the ends are free to vibrate. You strike that xylophone bar, it's gonna vibrate, and the ends are free to move. So this would be a free oscillation in the sense that both ends are free to move. But a string stretched out and tied down at both ends, that's fixed on both ends. So let's start by focusing on that. If you've got a string that's fixed in place on both ends, so those ends cannot move, what's the only type of interference that could be happening on the ends?
Destructive?
Right. The endpoints have to be destructive interference. And this interference, again, comes from the fact that as the wave is traveling, you pluck the string, you get this traveling disturbance. As the wave is traveling, its own reflection bouncing off of the other end of the string passes by it, and they interfere with each other, the wave and its own echo. So as they're interfering with each other, they have to make destructive interference at the endpoints because the endpoints are not able to move. So those locations that are always destructive, we call nodes. But in between those, we can also have regions that are always constructive interference, where you've got a crest from the wave and a crest from its echo passing by the same point and making a very large crest, or a trough from the original wave and a trough from its echo, creating a very large trough. So the locations that have always constructive interference are going to be very large oscillations, and those are called antinodes. So a node is a location where the string is just not oscillating at all because we get destructive interference. An antinode is a location where the string is oscillating wildly because you get constructive interference at that location all the time. And the simplest possible way we could do this, we've got to have nodes on both ends. The simplest example would be to have one antinode exactly halfway between, because they've got to be evenly spaced. And the way we usually draw this is by drawing the line up here and the line up here. These basically represent the highest that piece of the string can go and the lowest that piece of the string can go. And this is usually going to be drawn like this. And these curves here basically represent the shape of the string when it's at its highest up and the shape of the string when it's at its lowest down. The string is going to be oscillating like this with the two endpoints fixed in place. The middle can oscillate quite a lot. More towards the end, it's oscillating just a little bit. Near the end, it's oscillating only a tiny bit, and the endpoint itself is not oscillating at all. So this is basically representing the shape of the wave, the shape of the string when it's highest up, and the shape of the string when it's lowest down. This sort of oscillation, where you've just got a single antinode in the middle, this is called the fundamental vibration. Or is it the fundamental harmonic? I think it's just the fundamental vibration will be good enough. The fundamental vibration, in the sense that it is the simplest possible way this string could be vibrating as a standing wave. And we're going to be assigning n values to these. N in this case basically just represents which version of the standing wave we're going to look at. The fundamental vibration is called n equals 1. And then n equals 2 will be the next more complicated version of the standing wave, if we just add in a little bit more complication. And to do that, let's say we draw out that exact same string fixed on both ends. So we've got to have nodes on both ends. But how could we make a standing wave that's just a little bit more complicated than this one? What extra complication could we add in here?
I don't know how to like explain it, but it would be like with a part of the wave going up and a part of the wave going down.
Yeah, we could have maybe one part of the string. If you imagine splitting the string in half, I mean, not actually cutting it, but two sections, instead of the whole string bulging up and then the whole string bulging down, we could have half the string bulging up while the other half bulges down, and then vice versa. If we're doing that, if half of it goes up while the other half goes down and vice versa, what's happening in the exact center of the string?
It's like another node.
Exactly. The exact center would be another node. As the two halves oscillate oppositely, the exact center is not actually moving up or down at all. So this next more complicated version, the n equals 2 case, would be a node in the middle, one extra node. And of course, we're going to have to fill in the in-between zones with antinodes. From between node and node, we're going to get an antinode. Between this node and this node, we're going to get an antinode. And then if we fill this in, from node to antinode to node to antinode to node, and also if we fill in the underside, and again, this just represents the extremes of the wave. The extremes are going to be shaped like this and shaped like this as it oscillates back and forth. And you can actually see this. I mean, if you just take a guitar string and pluck it, it's vibrating too fast to really make out the motion. You just see it as sort of a blur. But the blur is going to be sort of shaped like this, or shaped like this. You can see it in much more detail if you watch a slow motion video of a guitar string. And you can probably find this online. If you just go to YouTube or whatever and search for slow motion guitar string, I bet you could find some good images, some good visualizations of what's going on here. These different standing waves that are possible are also called harmonics. So the fundamental vibration is also called the first harmonic. The n equals 2 case would be the second harmonic. And we could draw likewise an n equals 3 case. We draw out the exact same string, same length. And of course, we still have to have nodes on the endpoints. But instead of having one node in between, we could make this a little bit more complicated by having 2 nodes in between for a total of 4. And of course, they still have to be equally spaced. So we're basically splitting the string into thirds. So node, node, and then 2 nodes in between. And what do we have to fill in between the adjacent nodes?
There would be like
Antinodes.
antinodes.
Yeah, we're going to need antinodes between every adjacent pair. So we're going from destructive to constructive to destructive to constructive and so on, evenly spaced. Connecting those. And we get something like that. So this would be the n equals 3 case, or the third harmonic. And we could keep this going. We could keep drawing in n equals 4 case, n equals 5 case, and so on. N equals 4, we would just squeeze in one more node-antinode pair. Yeah, in this case, n represents the number of antinodes. But keep in mind that's only for this specific case. If the endpoints are both nodes, then n is the number of antinodes. I think more generally, a very good way of thinking of n is the number of half cycles. Like if you count up the number, not the number of complete wavelengths, but the number of half wavelengths, in the sense of like if you just got some wave, half of a wavelength takes you from node to node. Or this half of a wavelength, for instance. Half of a wavelength takes you from equilibrium to equilibrium. In this case, that would be from node to node. Note that here we've got 1 half wavelength corresponding to n equals 1. Here we've got 2 half wavelengths corresponding to n equals 2. Here we've got 3 half wavelengths corresponding to n equals 3. And then in the next one, n equals 4 corresponds to the idea that we now have 1, 2, 3, 4 half wavelengths. So generally, in this case of endpoints being this, if both endpoints are nodes, or also alternatively, if both endpoints are antinodes, n still represents the number of half wavelengths. For instance, if we go back to that xylophone bar, the endpoints are free to oscillate. The endpoints can wiggle around as much as they want. So the endpoints would be antinodes. And then in between, we could have any alternating pattern of equally spaced node, antinode, node, antinode. So let's say we have these antinodes, and then in between we have nodes. So this would be an example of a standing wave on a free vibrator, such as a xylophone bar, for instance. Anything that can oscillate with both endpoints free to move around. So in this case, we've got antinodes on the ends, and then in between an alternating pattern of nodes and antinodes. And so in this case, we wouldn't want to say that n is the number of antinodes. Instead, you could sort of think of n as the number of nodes. But again, I think it's more useful to look at n as the number of half wavelengths. Here we were looking at a half wavelength as the distance from node to node. But you could also think of a half wavelength as the distance from antinode to the next antinode. This is a half wavelength. This is another half wavelength. Because note that we're going from essentially crest to trough. That's half a wavelength. This would be another half wavelength. This would be another half wavelength. So we've got 4 half wavelengths, meaning this is the n equals 4, the 4th harmonic for this free oscillator. And we have to have a whole number of half wavelengths. If we have antinode on both sides, or if we have nodes on both sides, we've got to have a whole number of half wavelengths. Because if we had some fractional non-whole number of half wavelengths, like let's say we had 4.5 half wavelengths, that extra and a half wavelengths means that we wouldn't be ending at the same type of point we started at. If you want to start at a node and end at a node, or start in an antinode and end at an antinode, you have to have a whole number of half wavelengths or it doesn't work. And we can actually turn that into an equation. In general, for both of these types, whether it's fixed on both ends or free on both ends, as long as it's the same type of endpoint on both sides, we can write this out as an equation. These all fit the description that the length, let's say the length is L. So capital L is the length of the string. The length of the string has to be a whole number, n, of half wavelengths. Because each of these intervals from node to node or from antinode to antinode is exactly half of a wavelength. So we can say that in general, for any fixed region or any free region, as long as the endpoints are the same type of point, the length of the string has to be a whole number of half wavelengths. And that means we can now solve for lambda. And what do you get if you solve this for lambda?
You get 2L over N.
Yeah. And since n has to be a whole number, that means there are only certain wavelengths that will work. You could plug in n equals 1. We could say lambda sub 1. In fact, we generally call this lambda sub n, the wavelength of the nth harmonic. So if we want the first harmonic, also known as the fundamental vibration, the fundamental wavelength would be 2L over 1, or just 2L. The second harmonic, you're going to have 2L over 2, which you could reduce to L, but sometimes it's best to leave it as 2L over 2 without reducing so you can see a pattern emerge. Lambda 3, 2L over 3, or 2/3 L. Lambda 4, 2L over 4, or if you reduce, 1/2 L. And we could keep this going. 2/5 L, 2/6 L, or 1/3 L, and so on. In general, 2L over a whole number, which means there's only certain values of wavelengths that work. These wavelengths produce standing waves on that string. Any in-between values don't work because those wavelengths don't form a whole number of half cycles in the length of the string. So there are only certain wavelengths that make this work. The in-between values don't form standing waves. They might cause the string to wiggle a little bit, but it'll quickly die down because it's not a stable, sustainable oscillation. However, when you're listening to this, like let's say you pluck this string to create a sound that you hear, the wavelength doesn't really tell you what you hear. Because the sound, it's not like you have to put your ear to the string in order to hear it. The sound is traveling from the string through what else to get to your ear? What else is the sound going to have to pass through?
Air?
Yeah, the air. The vibrating string causes the air molecules to oscillate. The oscillation of air molecules is a traveling wave. Once that gets to your ear, it causes your eardrum to vibrate, and that translates into nerve signals that hit your brain, and you hear the sound. So the sound is traveling from string to air to your eardrum. And when it changes medium, the wavelength changes. So we can't really rely on the wavelength. But what doesn't change when the sound travels from medium to medium to medium? What's going to stay the same? The frequency, yeah. The amplitude could change. In fact, as it spreads, since this is a three-dimensional wave, the amplitude is going to get weaker and weaker as it spreads out, which is why sounds that are far away sound quieter. But the frequency will stay the same. The frequency tells you what note you're actually hearing. So instead of looking at this in terms of wavelengths, it's maybe better to look at it in terms of frequency. So let's convert this wavelength formula into a frequency formula. And what is the relationship between wavelength versus frequency? How are those tied together?
Velocity equals wavelength times frequency.
Yeah, we can always go back to speed equals wavelength times frequency. And we know the speed, in this case, this would be speed of the wave in the string, because the wave is being produced in the string. So the speed we care about is the speed the wave travels in the string. So we can plug in the formula we just got for lambda, 2L over N. And then how would we isolate frequency here?
Multiply by n and divide by 2L.
Exactly. We can just multiply by that reciprocal, n over 2L. Frequency is going to be V times n over 2L. So that is the frequency of the nth harmonic. And so just like wavelength, there were only certain wavelengths that will work here. There are also only certain frequencies that will work here. If you oscillate the string at exactly the right frequency, you get a standing wave. Certain frequencies work, other frequencies don't. So the frequencies that work, if we actually try plugging in n values here, so we can call this the frequency of the nth harmonic, we can calculate what notes you actually hear. So let's try running that calculation for the first few harmonics. N equals 1. F1, you plug in 1 for n, you just get V over 2L. And we call that the fundamental frequency. So that would be a note that you can hear from this string. When you pluck this string, you're going to hear this note. This is the pitch that you hear when you pluck the string. Of course, that's not the only pitch you hear. When you pluck the string, you're not really giving the string one specific frequency. When you just pluck a guitar string, you're causing it to vibrate chaotically at lots of different frequencies. But most of those frequencies quickly die off because they're not going to form standing waves. The only ones you actually hear, the only ones that perpetuate and sustain, are the ones that form standing waves. So you're only going to hear certain notes. What about F2? We plug in 2 for n. We could reduce that to just V over L, but I'm going to leave this unreduced for now. Just treat it as V over 2L times 2, because what did we already say about V over 2L? What is V over 2L here? Where did we just see that?
It's the frequency of the first harmonic.
Exactly. V over 2L is the frequency of the first harmonic, the fundamental frequency. So that means the frequency of the second harmonic is actually just 2 times the fundamental frequency, twice as high of a frequency. Likewise, if we take a look at the third harmonic, you plug in 3 for n, you get V over 2L times 3. But again, V over 2L is the fundamental frequency, the first harmonic. So the third harmonic's frequency is just 3 times the fundamental frequency. And likewise, n equals 4. we get the fourth harmonics frequency is just V over 2L times 4. And again, we could reduce this to get 2V over L. But I think it's more useful to leave it unreduced so we can see it's just 4 times the fundamental frequency, 4 times F1. And then we could keep going. We just get 2 times the fundamental frequency, 3 times the fundamental frequency, 4 times the fundamental frequency, 5 times the fundamental frequency, 6 times the fundamental frequency, and so on. In general, the nth harmonic is going to have a frequency that's exactly n times the fundamental frequency. So the notes that this string can produce, and remember, when you're just plucking the string, you're producing all of these notes at different levels of strength. Typically, the fundamental frequency is going to be strongest, and you're also going to get little bits of the other frequencies as well. This is the reason why when you pluck a guitar string or play any musical instrument, you get a rich, full tone. Instead of just hearing one frequency, which is going to sound horrible, if you're just playing one frequency only, it's just this flat monotone, and that's it. But if you've got this combination of mostly this frequency, plus a little bit of this frequency, a little bit of this frequency, and maybe a tiny bit of this frequency as well, you hear this richer, fuller tone that gives the distinctive sound to that musical instrument. A trumpet is going to have some certain ratio of these frequencies. A guitar trying to play the same note is going to have a different ratio of these frequencies. And so you're going to hear, even though it's the same overall note, you're going to hear different sounding sounds. You can distinguish between a guitar playing a G sharp and a trumpet playing a G sharp. They don't sound exactly the same because they're different blends of these frequencies. Also, since these are all nice, neat multiples of the original fundamental frequency, 2 times the original frequency, 3 times the original frequency, and so on, this is ultimately the reason why these notes sound good together. And if you look at the ratios, the theory of music is ultimately all about ratios. If you're going from F1 to F2, what's the multiplier there? Yeah, that's a ×2 multiplier on the frequency. And what happens to a sound when you increase the frequency? What would you hear differently?
The pitch?
Yeah, the pitch goes up. You hear a higher note. So in general, if you increase the frequency, you're going to hear a higher note. But this is a very specific increase. If you're doubling the frequency exactly, anyone know what happens to a note if you exactly double the frequency? If you precisely double it, you end up getting what's called an octave jump. The note goes up exactly 1 octave. 1 octave in the sense that it's the same, you might say it's the same note, but on the next scale up. For example, if I play a D, and then the D on the next octave up, that's a 1 octave jump. The difference between those two notes is that the frequency has been exactly doubled. And those notes sound good together. In fact, your ear basically interprets it as the same note, but the next higher version of the same note. Meanwhile, what about this transition? If you're going from F2 to F3, what's the multiplier here? What do you have to multiply 2 by to get to 3?
3/2?
Yeah, you're multiplying by 3/2, or 1.5. That's another nice, neat, tidy ratio. If you're multiplying the frequency by exactly 1.5, that's going up. It's going up less than an octave, but it's another nice, neat ratio of notes that sound good together. And if I remember correctly, multiplying by 1.5 is what we call a fifth. So that's going to sound like notes that sound good together. What if we take a look at F4? Instead of jumping from 3 to 4, I mean, we could jump from 3 to 4. What's the multiplier there? What do you multiply 3 by to get to 4? Yeah, you're multiplying by 4/3 or 1 1/3. Another nice, neat fraction of simple whole numbers. And that's going to be another jump, another increase in pitch that sounds good together. Something like, so that jump is a nice, neat frequency jump. And also, if we take a look at a different jump, let's say we go from F2 to F4, what's this multiplier? Times 2. Times 2 is another octave jump. So from F1 to F2, you're going up 1 octave. From let's say D to the next D. From F2 to F4, you're going up exactly 1 more octave, from D to the next D higher. So these notes sound good together because they are nice, neat, simple fraction multiples of each other. They're all simple whole number multiples of the fundamental frequency, and any pair of nearby frequencies are going to be nice, neat, simple fractions of each other. So this is the fundamental theory of why certain notes sound good together, because they're these nice, neat, simple fractions of each other. Any questions on that so far? So what if you want to adjust this? If I'm playing different notes, how am I getting those different notes? How do I make this create different notes? What am I actually physically doing when I want to change the note I'm producing? Like if I'm just going from to, I'm just lifting up some fingers, right? What happens to the pipe if I have uncovered some of these holes? Those are different notes because I'm producing, I mean, they sound different because I'm producing different frequencies. So this, that's a low frequency. That's a slightly higher frequency, a little bit higher. So I'm changing the frequency, but I'm doing so by uncovering more holes. What happens to the overall penny whistle if I've just uncovered more holes? What in this equation is changing? Yeah, I'm changing the effective length. If I've got all the holes covered up, the length of the penny whistle is the whole thing. If I've uncovered some of the holes, air can get out at this one, so the effective length is now only this long. If I change the length, I've made the length shorter. What happens to the frequency? Length has decreased, so frequency yeah, the frequency increases. And you can hear that as I uncover more holes, the frequency increases. So a decrease in the length increases the frequency that's produced. And vice versa, as I cover up more holes, covering up more holes increases the effective length and therefore decreases the frequency you hear. You can also adjust this by changing the velocity, but that's kind of difficult in the case of a wind instrument because we're talking in this case about velocity in the air inside the pipe. And velocity of air depends on its density and its temperature. So that's not really going to change unless you change the climate. Maybe you move to a different room with hotter or colder air. But the velocity in a wind instrument doesn't really change, but the length you can change by covering or uncovering more holes or sliding the mouthpiece outwards or inwards. On a stringed instrument, though, you can change the speed. How do you usually tune a stringed instrument, like a guitar or a mandolin or a violin or whatever? Like if your guitar is out of tune, how would you change that? How would you put it back in tune? Yeah, by turning the tuning pegs, you're tightening or loosening the string. By making the string tighter, and note that you're not changing the length. The distance from tuning peg to bridge is still the same length. But you're changing the tension, and changing the tension changes the speed. So you're keeping the length of the guitar string the same, but by changing the tension, you're changing how fast the wave travels. Faster speed means a higher frequency. So you can adjust the note that the string produces without even changing its length. So this is the physics behind why music works. Every musical instrument that's creating certain notes is using this sort of physics in order to do it. Any questions on that? All right, have a good weekend, and I will see you next time.